All right, let's start. Okay, good. All right, hello, welcome everyone. This is ECS 277, Advanced Visualization. Happy to have you in this class. Happy to learn from you, and happy to be able to teach you. I hope that most of you had some kind of experience or exposure to graphics already in visualization. Have to ask this: who has not had an introductory course to computer graphics? You had some computer graphics programming.
Yeah.
Okay, ray tracing, OpenGL. Okay, so you all should have a very good background and experience with OpenGL, GL programming, graphics libraries, rendering, shading, all of that. That's the basic for all of this, okay? I will not review any of that. Phong lighting models, ray tracing, all of that, you really should, that should be, I mean, in your sleep, you should be able to do that. Even better if you have had some advanced visualization course like volume visualization from Professor Ma, but at least the introduction to visualization, 177. Who has not had an introduction to visualization? Okay, so many, all right. So I will review everything that is said in Introduction to Visualization in the first 2 or 3 lectures, so don't worry, I will cover it. The essential stuff that you need for this class. This class will not be about making the pretty pictures. This class will be mainly about the underlying mathematics and fundamentals to make meaningful and correct pictures, okay? So there is first the art of making expressively very nice and good-looking pictures from an aesthetic point of view, and then there is a scientific side of the whole game. That means you have to produce pictures which are really meaningful, correct, and can be quantified in terms of the error that they carry, right? So I'm more about the mathematics, the fundamentals, the algorithms, the geometry, and all of that. So therefore, when you do your assignment, it's not so important to worry about the greatest looking movie or the greatest looking picture. It is more important for you to impress me that your program is actually correct. And the picture I'm looking at, even if the interface is not superb, that the picture I'm looking at is a correct picture. That's what I'm after, okay? Because otherwise, if we as scientific visualization people produce great pictures, but they portray the wrong information, then it's meaningless for the scientist, right? Or the policymaker, or the engineer, right? Whoever our audience is. All right, enough talk. Let me get to know you a little bit, at least by name, tonight. First, so Jennifer Chandler. Jennifer, hello. Bill Dawson.
Here.
Hello. Beth Carolina, hello. Kevin Griffin, Kevin. All right. Oh, he's the one at Lawrence. All right. Stuart, hey. Hello, Stuart. Catherine Isaacs, Kate, hello. Kong Hao, Jiang. There you are. Hello. Jinju Lu. Hello. Sean Recker. Hello, Sean. Carlos Rojas. Hello, Carlos. Tim Severins. Tim. I think he just enrolled recently. So, Zira Shah. Okay. Misha. There you are. Shashkov, right? Is that correct? Okay. Minchi. I had a colleague who had the very same name, Minchi. When you look him up, he is in computational fluid dynamics. Minchi. Okay, and he now, I think, is either in Tennessee or in Alabama, working for a big research center for fluid dynamics. Min-Chi. Same spelling, everything. Okay. Nick Todman. Hi, Nick. Do I say Nicholas or Nick? Or? Either is fine. Okay. Chunfu Wang. Hi, Chunfu. Do I say that right? Correct? Chunfu? Okay. Yang Wang. Is it Yang or Yang? Yang, okay. Yang Xiao Wang. Yang Zhao, is that correct? Close enough? Okay. Zhucheng Wu. Hello. Meng Xi Wu. Meng Xi? No. Yukong Ye. How do I pronounce your first name? You? Just you. All right. And Fernando Fuentes. Fernando? No? All right. Okay. My name is Bernd. You can call me Bernd, of course. This is informal. This is about teaching. I don't want to have any barriers between you and me. You can always ask me questions by email about anything, but even better, since your questions are his questions, your questions are better asked here in class, okay? It doesn't help you if you send me an email that answers a question for you and you know the answer, while your fellow buddies you also could benefit from the answer, okay? So best thing is at the beginning of class, always ask questions about the stuff from the class before. Or during the lecture, when there's a question, you ask it. Don't be shy. Who still needs a syllabus? Okay, the two of you. All right. And so this is the first that I would like to do. After class, there will be some handouts. Don't run away. Okay, there's a bunch of things for you to read this week. Okay, every week I will bring a big bag of presents. And these presents are the research papers you have to read, okay? Now, these are the papers for most of the class. In addition to those papers, I will expect you to also read other papers, and we'll talk about that. You will be doing well in this class and shouldn't have too many problems with the assignments. It's heavily weighted on the assignments, this class, if you have a good, solid background in computer graphics, programming, and a good understanding, also from the programming perspective, of basic visualization tools. There's only three things, right? Slicing, contouring, and raycasting. The rest is just icing. And if you have a good appreciation of the underlying numerical methods and the mathematics and the geometry, okay, then you will be fine. And then it's just a matter of attitude, putting the time in, okay, for the assignments. All right, so let's go over the syllabus. We meet here on Tuesday and Thursday nights, and I know that we have some participants, hello, remote participants at Livermore, watching us from Livermore. Therefore, we all have to speak into the microphones whenever we have a question, okay? So whenever you say something or ask a question, you have to speak into the mic, speak into the mic, speak into the mic. Otherwise, only I hear it. The assignments, how do we do that? I want to see the great projects you are doing yourselves, myself. And the easiest for me is, and I hope also for you, to just show me your projects after class. Okay? For those of you, this is not possible, we work something out. But in general, I would like to see everyone's project, say, for 5-minute demo time after class. So Tuesday nights from 7:30 to 8:30, I can see 12 demonstrations, and Thursday night I can see 12 demos, right? And you just pick the best time, the best day that works for you. If neither Tuesday or Thursday night works for you, then we do something else, okay? Office hours are Tuesday mornings. You can see me in my Kemper Hall office Tuesday mornings, and pretty much only Tuesday mornings because I have to move around a lot. But again, if there are a general question that you have, you just ask them in class, okay? I will be happy to take any question in class, and again, if I answer, it will benefit everyone if everyone hears the answer that I have to say. There's one essential textbook that I think you all should have anyway, whether you take this class or not. Since you specialize in visualization, you should have the text called the VTK book, the Visualization Toolkit book. And also, since this class is really about the underlying geometry, the modeling of curved surfaces and volume data, you should have this book by Farron, the Curves and Surfaces book. And most of the papers that I recommend to you to read and that I will hand out are papers from these three most important venues. One is the IEEE Visualization Conference proceedings. The other one is the SIGGRAPH proceedings. And then the other one that you all should read regularly are these transactions on visualization and graphics, computer graphics. So there are really three main objectives with this class. Okay, I say the objectives are blah, 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 blah. There are really three. The three main objectives are A, to learn about the underlying geometric modeling concepts, the approximation, the interpolation, and the representation of the data. Okay, how do I approximate the data in a good way so that I produce a meaningful and mathematically correct image? That's the first objective. Second objective is to really deal with large data, big data sets. how do I apply my visualization techniques to big data sets? And when you talk about big data, you have to talk about compression, hierarchies, abstractions, etc., etc. So that's the next thing we talk about. Once we know how to approximate it in general, then we talk about how to use these schemes to actually do it in a hierarchical fashion for big data sets, right? That you cannot manage all at once, but you have to deal with it piece by piece or in coarser resolutions. And then last but not least, the most important issue is the challenge of big data. It is not sufficient anymore to make a picture of the big data because the big data is so big that you need a screen that is as large as the United States to see it all, right? The computer screen is just too small to show everything. There is so much data now that even if you produce the best, coolest raycast image, you cannot put it on a computer screen. The screen needs to have the size of the entire globe to show it all. That's what it really means to deal with petascale data sets or exascale data sets. So we have to worry about, well, if I cannot make a picture of everything, I have to worry about making a picture of something. So what is the something that has meaning, right? So then we have to talk about big data set. What is the important dot, the important point, the important feature, the important aspect in it? And so this translates into the issue of feature, pattern, recognition, extraction, etc., etc. And so this then goes into the area of pattern recognition, feature extraction, feature visualization, etc., etc. Assignments. The assignments are very important. They are time intensive. So do not fool yourselves. The assignments require a lot of time. I did them all myself at one point when I was 40 years younger. And if you force yourself to dedicate a certain amount of time every day to it, half an hour, 1 hour, concentrated, no problem. But if you want to make these assignments work, beginning 2 days before the deadline, you will fail because it just requires time, debugging, finding the bug, right? The thing crashes, where's a pointer, right? Divide by 0, you don't find it, it takes time. So begin with the assignments early on. And there will be 3 assignments coming from me, and there will be 1 assignment that you give yourselves. 1 assignment comes from you. And so since that will be the really demanding and challenging assignment, that last assignment, number 4, will have twice the weight as all the others, right? So all the first 3 assignments have 20% each, right? So 20 plus 20 plus 20 makes 60 points. And the last assignment that you pick yourselves is 40 points. Okay? And again, the first 3 assignments I give you should be the first third of the quarter, the second third of the quarter, the last third of the quarter, right? That's about the time that you need for the 3 assignments I give you, about 1/3, 1/3, 1/3, 3 assignments. The assignment that comes from you should require the entire quarter. Why? How do you start with your own project? Well, you first have to read something, right? You have to, what is this last project I want to do? You cannot figure that out the week before. I mean, you should already think about what is cool, what's exciting, what would I like to do that is related to all this stuff, right? How to make a scientifically meaningful picture. Think of something. In order to think of something, you have to look at books, look at proceedings, or look at websites or whatever, or think of something inspiring. But this idea doesn't happen overnight. You need some think time, right? I mean, think about it, read about it, and then maybe after 1 or 2 weeks, you have this more crystal clear idea of what your last project should be. So you need to start there, right? Read a lot, think a lot to come up with the idea what your own assignment should be. About 2 or 3 weeks into the course, I will ask everyone to give me a little paragraph. Can be very short, 2 or 3 sentences where you say, Bernd, this is my final project proposal. I want to do this, this, and this, and at the end you see a movie that shows that. Boom. And I will say, that's great, go ahead, do it. Or I will say, wow, this is way too ambitious. You need 100 people to do that in a year. And I scale it back. Or I say, wait, this is so simple, it takes 5 minutes. Don't do it. Anyway, so in about 3 weeks, you should be very clear about the direction. And after that, you should start with prototyping things for your own project. And the last project also will require you to give a presentation about it, because no one knows about this final project besides yourself. Only you know. So all the other students should benefit from that, right? So the last 3 or 4 lectures are not lectures given by me, but they will be lectures given by you for your buddies and for me. So I can learn something too. Right? Grading. Typical grading, I have to put this on paper, right? So more than 90% gives an A, more than 80% gives a B, etc., etc. And I would like to stick to this course being a pure programming-oriented course and research-oriented course where everything is driven by the assignments. Particularly the last assignment that comes from your end is really a research project. Ideally, I would like it to be something that you work on anyway in the context of your research that you're already doing, that you want to do. So this class doesn't take away from your research, but it kind of like it builds on it or complements it, okay? So of course, the first thought that should come to mind is, okay, well, Bernd asked me to do this and that and gives me the freedom to pick my last project. You should pick something that relates to something you are working on with your major professor anyway, so then everyone is happy, right? It's not a waste of time. Then you don't do the final project just for this class, but you also do it for your next research papers with your major professors, right? And that's of course fine. No problem. The project grade will be driven by 4 components, and it's mainly driven by, is the assignment actually complete? Are you doing everything that I ask you to do per recipe, right, per assignment? Is it correct? Do all these different things that I expect you to do correctly, are they running correctly, yes or no? And then how good is the interface and how good is the manual? I want you to also write a little user's manual, half a page or 1 page, where you say, if you want to run this program, you have to press this button, type in this command, boom, 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 and you will see that picture, okay? But again, the emphasis lies on correct algorithms, correct implementation, and that you try to tackle all the things, all the elements of the assignment, okay? Again, interface quality, I don't want you to spend too much time on that. Interface quality and the best and most perfect human-computer interface can absorb all your time, okay? You just work on that, but don't do that. Worry about the fundamental algorithms. That's the most important part, okay? Tentative course outline, I will talk about that later in class, so I don't have to read it from this syllabus. Then let's go to the next page. I gave you a list of mandatory reading of books. These are just some of the mandatory books that I think everyone who is pursuing a PhD or graduate degree in computer graphics, visualization, geometric modeling should read. Okay? If you pursue a PhD in any of these areas, this is the basic library that you really need to have. Okay? So for this class, the core, the important books are under the rubric visualization. But equally important to that are the books under geometric modeling, because I will talk a lot about the geometry, how to do the approximation and the interpolation of the geometrical primitives that we need to work on in order to make the visualization really correct. Okay? These are the most important things. And then the other very important aspect for all of you being graduate students is the bottom part, journals and magazines, right? This is like Olympic Games. Graduate studies is done in competition. You want to win, right? You need to know what the competition is doing. The competition is publishing in conference proceedings, in journals, and transactions. So you as PhD students, you have to every week force yourself to read what's going on in my community, right? If you specialize in ray tracing, you have to be aware what the other people are doing in ray tracing. If you specialize in contouring algorithms, right, or 4-dimensional functions, you have to know what people are doing for contouring hyperfunctions, right? You have to know that. So these are the journals and magazines that you should skim, and you should read those articles in it that relate to your research. So it's a general recommendation or general advice. If you specialize already in a particular area of graphics, visualization, computational geometry, or something like that, then you always have to read the literature, the best literature, the highest impact factor journals and proceedings in that area. Okay, next page, I give you some analytical test functions for one assignment where you need that for vector fields. And so I understand these functions pretty well, so I know what kind of picture should come out. Okay, that's why I give you this. Next one is actually assignment number 1. And I encourage you to glance at these assignments tonight, tomorrow, and so you have an idea about the programming effort involved. And again, the top portion of each assignment spells out what I expect you to do, and then additional credit. These are just some ideas of things that you might consider doing, okay, on top of the real assignment. But then again, you also get additional credit for adding your own ideas. In fact, I really want you to think about your own ideas, okay? These additional credit thoughts are my thoughts. It would be much better if these additional credit thoughts are your thoughts, okay? Again, I'm very flexible, very open. Also, I want to say this in public, if a certain part of the official assignment just doesn't work out, it just always crashes, just always fails, whatever, feel free to come up with a substitute idea that comes from you and say, hey, Bernd, this thing I never figure out how this aspect of the transfer function thing works. I can't get it to work. Therefore, I added this additional idea. Is this cool? And I say, yes, it's cool. Okay? So again, I will be very flexible when it comes to interpreting these assignments. The grading, the grading will be interactive grading. I want to see what you are doing, and I want to see it myself. And again, ideally, directly after the lectures on Tuesday and Thursday nights. Okay. Again, if that doesn't work at all during these hours after the lectures, then we have to work something out. And about 5 to 8 minutes demo. Okay, so the demo then really means you have to have a bunch of snapshots, image snapshots already there. Okay, I cannot sit there and wait for 10 minutes with you on a raycast image, right? Which big petascale data set and you raycast it and we wait hours to can't do that. So I would like to see how you start your program, how you run your program, and I want to see some pre-generated output, right? That your program produces after 5 minutes, 5 hours, 10 days of operation. But I cannot wait there, right? So I just want to say, Bernd, this is what the program looks like when I first started. These are the parameters we can play with and the knobs and dials and buttons. And then maybe if it's a real-time application, yes, then you can show it to me in real time. But if it's a program that requires really minutes to generate a high-quality volume rendering, then you have to have some screenshots, okay? And show me 10 screenshots. Okay, so because I only have 5 to 8 minutes per demo. It's just a fact. All right. Best thing is, for flexibility, you demonstrate your programs to me on a laptop, so it's portable and we can look at it wherever, either here in this classroom or in my office or in the basement of Kemper Hall, whatever, okay? Think about that, whether this works for everyone, okay? I know that some of you might have to connect to a remote server or remote machine, but still, I cannot run around from this building to 15 other buildings. Again, it's practically not possible. So if you need to show me something where the big data or the big images or the application runs somewhere else, I still have to see it through a portal on your laptop. Okay, think about that. All right. Everything clear so far, or any questions? Or shoot, your question is his question. No? All right. Okie doke. Anyone still needs a syllabus? Okay.
Will you be using SmartSite at any point?
No, not at all. You come to a lecture, and this is it. You should get all the answers and all the great questions. The questions are more important from this class. And also, I will not make this recording available to students who can be here physically, except those who are remote participants, okay? Why? Well, I guess you know the answer why. Because I like you so much and I want to interact with you, right? So anyway, I also don't want this to be too stiff, and I do not want this to be a monologue. You have to open up, you have to ask me, okay? When I'm going too fast, when I'm going too slow, when I tell you something that's boring or whatever, okay, when something is not clear, you jump in and say, Bernd, this is incorrect. When I'm doing a mistake on the board, you have to tell me. I'm an old man, I make many mistakes, right? And you have to tell me, Bernd, this is wrong. I'm used to that. All right, so today I give you a brief overview of the things that are going to hit you, that you will be able to enjoy. Some of the things already should be familiar territory to you, some of the things I will be hitting on allude to some of that stuff to come. And again, since we are so many in this class, the last 4 lectures probably will be lectures given by you. We will probably have about 20 students. And so last 4 lectures, that means 5 students per lecture will have to give their presentations, right? So that means everyone will have to give about a 15-minute presentation, right? So lectures 16, 17, 18, and 19, 20 or so, last 5 lectures will be lectures given by you. Also plan on that, okay? And to be fair, I just go by the alphabet, right? In reverse order. I know in normal order, okay? So, I mean, think about that, okay? I have to have some mechanism to do that. I just think alphabetically, I do it alphabetically, right? If you are Asimov, then you go first, right? Right? And so forth. But then if you want to deviate from that order, you have to figure it out with one of your buddies whether someone is willing to swap with you. I don't want to be involved there, okay? If you want to swap your time and you say, I mean, Isaac, I'm simply not done, can you swap with me? And Isaac is nice enough to swap with you, then you swap. Okay, no, that's fine. Okay. Overview, formats. There are no questions? You have no questions? It cannot be. That cannot be. I have so many questions. The older I get, the more questions I have. All right. So let's talk about survey. And let me ask the camera operator. Camera operator, is it big enough? Visible? Cool? All right, she says, okay, good. So data. So what does data mean? Data means, what does the word data mean? The word has a meaning, right?
It means information that's been collected that's of interest.
Interesting, but no. Do you know this? This one? Dara is the infinitive, right? Means to give. Datum is the given one or the given thing, and data are the given things. That's what data means. Data means the given things. That's the stuff given to us. There's no information yet. There's no insight yet. This is just the given stuff. Data is the given stuff, the given things. So what does this mean in scientific visualization, to be concrete, right? In SciViz, what do we have? What are the typical things that we operate on? One-dimensional things, two-dimensional things, three-dimensional things, four-dimensional things, right? That's it? Physical data, right? There's physical data. Physical data, right? What else is there? There is abstract data. Okay, what else is there? There is high-dimensional or multidimensional data, high-dim, multi-dim data. There is scalar field data, vector field data, tensor field data. All this is a big mishmash of stuff, right? And you have come across some of these. There's scalar, vector, tensor, data, and much, much more. But in this class, of course, we will stay mainly in this domain, right? Data sets that have an inherently physical interpretation that characterize the physical world around us, or the simulated physical world around us, that have a meaning, a physical meaning. like space, like time, like temperature, like flow, like strength, like force, etc., right? So physics, and physical data. Abstract data, what's that? Much more higher to define, right? High-dimensional data, multidimensional data, what is that? How high is high? What is high-dimensional? Scalar field, vector field, tensor data. Then you have these other kinds of categories. You have univariate data. Univariate, if there's univariate, there's also bivariate, right? There's bivariate. There's then also trivariate, and then generally multivariate data, right? Trivariate data. What does this mean? Univariate, bivariate, and trivariate data. The meaning is hidden in those words, right? It's a data set that depends on one variable. This is a data set that depends on two variables. This is a data set that depends on three variables. So examples for this: if you have a function f, if f is f of x, then you have one dependent variable, right? One function fct and one variable. Okay, so this is univariate. Okay, then a generalization is multivariate. You have one function, one dependent function value that depends on multiple independent parameters, and then you number them from 1 up to, say, xm. Okay, so this function, this value f, depends on a bunch of inputs. This would be multivariate, right? Multivariate. It's very hard to make a picture of that. Can we make a picture of that? Up to m equals 3 or 4 maybe, okay? As soon as m is 5 or larger, then we already are stuck. So what next? Then you also have these things where you do not have just one variable being the dependent one, but multiple, right? So then you also have things like this. Then you have one function that depends on one variable. So you have vector-valued functions. One function, first function, that depends on x, and the second function, f2, that also depends on the same input. Now this is a multi-valued, right, function depending on one variable, right? So this is a multi-valued univariate function, fct. Okay, and so the most general case of function that we will come across are, of course, where you have multiple dependent variables depending on multiple input parameters. How to make picture of that? So it becomes more and more challenging. So you have the function 1 up to some function n, and each function depends on m variables, x1 up to xm, and the last one also depends on x1 up to xm. Okay, so this is a multi-valued, multivariate function. Multivariate, multivariate FCT function. In this class, we will live in the very simple cosmos concerned with the stuff up here, right? We probably will barely touch on this, right? But you should think about that, okay? You should think about what this means when you have more and more variables and more dependent, independent variables. What it means, even what is the independent, what's the dependent variable. If you just have data, you do not know which ones are the dependent and which ones are the independent ones. Even to separate which are the independent ones, the x's that do not relate to one another, and which are the dependent ones, the f's, that usually you don't know that, right? You just have a bunch of input measurements. So, data. So this is very important to think of in terms of formats. And this is just physical applications. Now I go down to a very simple world of this simple world of physical data sets. What types of structures or grids or meshes or representations or connectivity forms have you come across so far? Data can be given to you in what types of format? File format, organization. Tell me. You know that. Shoot.
At volume data sets, just a big tensor, and I get intensity values for each coordinate position, and you can use that for volume rendering. So I've seen that before.
Okay. I just absorb. Okay, you tell me, and then I try to synthesize it. Okay.
Yes. I was just thinking something simple like a table or a matrix.
Table, matrix, good. All right. Give me more. Shoot. Come on.
Maybe give you a set of abstract functions.
Abstract functions.
Or, well, I mean, but I mean abstract function, x squared plus that kind of thing.
Okay. Abstract functions. I like to be concrete today. Right? I just have a point. I just start with points in this room, x, y, z, and I have a measurement there, right? What are the things that I can measure there? Temperature, flow field. I can measure it at this point, at this point, at this point, at this point, at a bunch of points, right? So that's the format. If I just have a bunch of sensors, measuring devices in here, then what's the input set? It's just a bunch of points, right? That's the most primitive form. Most primitive form, I just have points, right? So the format of the representation is just a point set without connectivity. But now you already alluded to something that's the volume. There seems to be some structure there, right? Okay. And Kay talked about tables. Also, there's some kind of index there, some organization, some first, some last, also some index, right? There's also some structure there. So from points, you can then also worry about the connectivity among the points. And sometimes the connectivity is implicit, right? On the x-axis, point 1, point 2, point 3, we order them automatically from left to right. That's an implicit connectivity, right? 1 is connected to 2, 2 is connected to 1, to 3, and 3 to 4, and so forth. Also in the volume data set, when you index things, there's an implicit connectivity there, right? Point 0, 0 is connected to point 1, 0, 2, 0, 3, 0, right, and so forth. In the volume data set, the same thing. Point 0, 0, 0 is connected in the opposite corner with point 1, 1, 1, etc., right? So the index induces a connectivity. So this is the issue of points, connections, meshes, grids, structured meshes, unstructured meshes, hybrid meshes, and ultimately triangulations or tessellations in the most general form. Okay, so these are some of the formats that you run into. So the most simplest form is gridless data, right? Gridless data or meshless data, right? Gridless or meshless, or also sometimes called scattered data. Okay, gridless, meshless, scattered, all the same. I'll just give you an example in 2D, and I become more and more concrete as time goes on. This is just a bunch of points without order, completely randomly distributed, and so forth. Huh? So here you just have a set of xi's, yi's, and maybe a function value there, right? And maybe you have n of those guys. That's it. This is a concrete instantiation of that concept. So this is the first. Now I give you just an evolution in complexity, so increasingly complex representations or meshes. The simplest one that you were probably thinking of were Cartesian meshes. 0, 0, 0, 1, 0, 0, 2, 0, 0, and the one up there in the corner is MNK. So those are Cartesian meshes. And again, I just sketched them for the two-dimensional simple world, xy. So the simplest one is Cartesian. Why are they called Cartesian? Do you know why that's called Cartesian? If you don't, look it up. All right. So Cartesian has an underlying implicit structure of this geometry. This geometry is not stored explicitly, it's there implicitly, because you call this location 0, location 1, location 2, location 3, and so forth. And this is also location 1, 2, and so forth, right? So for the points, for these particular points, you do not really need to store the x and y. It's there. It's the integer index, right? So this one. Then what is the first generalization of that? First generalization is rectilinear. Where a mesh would look like this. Okay, it's obvious what the difference is. There's some spacing, right, of non-uniform character. I don't need to write this down, you see it, right? Rectilinear, why is it still called recti? Something is rect or rectangular. What is it? The intersection of these things, right? It's still right angles everywhere. That's why it's still called rectilinear. And why is it linear? Because the connections between the points are still linear, are lines, right? That's why it's called rectilinear. So the next one, now it becomes a little bit more general. This is called a structured mesh, where the geometry would look like this. Okay. You see that that's the generalization of that, right? Now for this one, obviously, you need to store the coordinates x, y of the points, because they are now floating point numbers, real numbers, right? Okay. And now I just give you the most general hybrid. A hybrid thing can look like this. Okay. It consists of all kinds of cell types, grid types. So in this class, we will have to worry about making pictures from data like this, data like this, data like this, maybe data like this if you choose to do that, okay? It's all clear? Makes sense? So there's an entire discipline which is called grid generation. Grid generation. Where people worry about how to represent this room by a bunch of cells, okay? If I give you a description of all the geometry in this room, of all the microphones, of all the pens and pencils, of all the water bottles, and of all the human beings in it, right? Then how do you put a bunch of bricks, a bunch of cells in this empty space between the geometry such that the entire space is covered by those cells? How to do that, right? We as scientific visualization people take that as given. It's a data, right, for us. Huh? But some people actually have to generate that first. Interesting question, right? Why do you need to do that? Why need to do, because you do simulation, right? Some people do computer simulation of the flow in this room. There's an air conditioning running, right? If you want to do that, well, you better are able to fill this room up with a bunch of tetrahedra and cells and hexahedra and whatnot, and then you do your simulation, and then you can make a picture of it, right? So people who do the simulation, they have to worry about that and spend a lot of time on producing the grid cells. Modeling. We actually, as I said, we have to worry about modeling. This is the focus of this class, really. Modeling. And we do this for curve data, curve or 1D data. Okay, where the application looks like this. We have a bunch of locations with a bunch of sticks or measurements. Typically, that's our input, right? Our input is discrete stuff, finite stuff, certain points, certain locations with some measurement there. Either it was a measurement or it's the output of a simulation, right? We don't really care. It's data. And do you make a picture of that? Well, yes, you can. That's a picture, right? You just show the raw data. That's what it is. But that picture isn't pretty, right? In order to make a pretty picture, you need to do that, right? Then you make a picture of that. It looks better. Okay? So if we do that for the curve, we also have to do that for the surface case or the 2D bivariate case. So what does the scenario there look like? Here it's an x, and here we call it f. In the 2D case, we call it x and y, and we call it f going up. And what do we have here? Well, here we still have a bunch of locations and still a bunch of sticks, right, which go in the function direction, like this. Okay, that's a picture of the real stuff. If these 9 points and these 9 measurements are all that we are given, that's the real picture, that's the truth. But we don't accept that. We want something reconstructed that looks like this, right? Okay, and then we render that. Okay, how do we do that? That's all covered in this word modeling. The modeling means, given some finite or discrete input, how do we get a continuous, a continuum representation back from it? And then, of course, we really will be concerned with the volume case, volume, or 3D trivariate data. And what's the situation there? Well, I can no longer draw it, right? Why can't I draw it any longer? I can draw this easily, right? This is already a projection I'm drawing. It's already a projection of something that lives in three-dimensional space onto the flat board, right? The next thing I cannot really draw anymore. So I can only allude to it and say, okay, so my data space itself is already three-dimensional. That's my x, y, z. And the function is another direction, right, which I cannot draw. So my data space would be a volumetric domain, right? And I have maybe some samples given here, right? And I need to construct a continuous function over this set of bricks. Huh? So here I could be given as input a bunch of xi and fi tuples, n of them. Here the input would be a bunch of xi, yi, and fi tuples. And here the tuples would be actually quadruplets, right? So here the input, or the given, or the data, would be stuff like this. It would be x's, y's, z's, and at least one dependent variable, right? And how do we get from the finite and discrete to the continuum? In most of visualization, you can get away with really just one type of a function for interpolation or approximation. What is the most important interpolation scheme that you have learned so far or heard of and used over and over?
Linear. I've used linear.
Linear. You can, if you understand linear interpolation in all its forms and all its beauty, that's it. And when you use it for a line, it's called linear. When you use it for a surface, then it's bilinear. And when you use it for volumes, it's called trilinear. And when you use it for time-dependent volumes, then it's called quadrilinear, and so on. But you really only need to understand how to interpolate along a line. Huh? One value, another value, and what's the value in between, assuming a linear or line variation. That's all you need to understand. True or not true? Not true. Right? Because is the world a line? just using this mathematically idealized world of lines, bilinear functions, trilinear functions, is a way to make a picture. But you should really use the type of a function that is appropriate for the type of phenomenon that you want to model or represent. Nevertheless, for most visualization applications, it suffices to use lines, bilinear elements, or trilinear elements, okay? Okay, all right, so all you need is lines, right? Linear interpolation, lin int, okay, with a big question mark, because this is probably not true. So linear interpolation is this. I give you x, I give you two locations where I have measurements, 1 and 2, and I want to evaluate here. How do I do that? I consider circle and circle and put a line through there, and then evaluate the line at this location. And I get that value, f at x bar, right? That's linear. Huh? All right, what is bilinear? Bilinear, well, it's bivariate, but it uses linear variation in both directions. How to think of that? Okay, let's see. So you have 4 points. You have, say, 4 values at these 4 points. Okay. Here you wanted to know a value at that location. Here you need to know a value at some location in the interior here, maybe here. How do you do that? Well, first you use linear interpolation for the sticks in one direction, say in this direction, duck and duck, and you want to evaluate here, okay? Okay. So you use line, and then you evaluate these lines at this location to get these guys. And you obtain these. Okay. And now you need to do another line or linear interpolation in the transversal direction, the other direction. Right? Now you want to evaluate here. Okay. How do you do that? You take this line and now evaluate that line here. And you get that final point that lies on this surface there. Okay. So that's called bilinear. You apply the line paradigm twice. First in the x direction and then once in the y direction. But it's just lines. Okay? So for trilinear, you do the same. In the trilinear case, I cannot really draw it like that because I cannot make projections of 4D space easily. Trilinear. Okay. So in the trilinear case, the domain itself already is trivariate, and we call it x, y, z, and you have some kind of domain cube. And you want to evaluate it at some location. So first you would evaluate linearly in x to get, say, these points. Okay, you evaluate linearly in x from here to here, evaluate it in a linear way to get that value from here to here, and you get a value here, and then you do the same. This guy and this guy gives you this circle. This guy and this guy interpolate in a linear way gives you this, and this gives you a quadrilateral, right? A new quadrilateral which lives here. And now you evaluate this guy for, say, some y value here, and this y value, say, is here, this guy, and you get a new line here. And last but not least, you evaluate that one line in z for, say, the midpoint, and you get the value there. Right? So you do 3 times the linear interpolation. You interpolate linearly 4 times in x direction, then twice in y direction, and then the last step once in z direction, right? 4 to 1 as a pattern, right? Once 2 plus 1, and here it is 4 to 1. Huh? You see that? It gets very expensive when it becomes more dimensional. That's the explosion of dimension. You see that already? Okay. That's enough of that. But anyway, the important part is all you need is linear, right? This is all just linear interpolation. This is a fundamental thing that you need to understand and know how to do well. Then everything is fine. Is it? No, it is not. Okay. Why is this good or not good enough? Let me put up one example. Okay, this is a linear versus quadratic. Okay. I'd give you a very simple example that most of you will understand, whether you had visualization or not. And so this example is just contour lines. The example is an example of contour lines. If I give you a bunch of triangles, and I give you values at these points, say I give you a value here, I give you a value here, and I say that bullet is value 1 and circle is value 0, and I want to find a contour for a threshold 1/2. Okay? So I have a bunch of triangles. I have triangles with 3 corners. At each corner I have a value. I have either the value bullet or circle, 1 or 0. So where's the contour 1/2? Where are the contour points for 1/2? Where are they? Shoot.
Just the midpoints.
The midpoints, yes.
For each of the
Right? 0, 0, there is no 1/2. But 0 to 1, 1/2 is in the middle. Okay? So I get the contour points at the midpoints of all these guys. How would you then render the iso line or the contour line? By connecting them. Okay? There's always 2 steps, the contouring algorithm. Always look at the edges in your mesh, find where contour intersect the edge. Once you have those points, you have a strategy to connect them. Okay? That's the way to look at them. And here, well, you connect it like this. This is a contour. Is this a great and beautiful contour or what? It's great, right? Is it nice or not? That's its job. Okay, but I can give you a nicer one, right? So this assumes a function over each xy triangle to be of the form a plus bx plus cy. Okay, that's a linear function because x and y only come up in the to degree 1, power 1 there. Okay, that's why it's linear. Now I give you the same configuration. Okay, and again I say this is a value 0 surrounding a center value of 2. Bullet is 1, and circle is 0, and I want to find contour for threshold value being 1/2. Okay, but now I assume a variation of each triangle f of xy equals a much more complicated thing, namely a plus bx plus cy plus dxy plus ex squared plus fy squared. Okay, I go to higher degrees. And you have to believe me that when you evaluate that, you will get a contour that looks like that. Is it nicer? Is it better? Which one is correct? Well, that depends on the underlying assumption. If nature says nature behaves in a way like that, then this is correct. But if the underlying physics say, well, nature really requires us to make a smooth picture, then we should do that. It depends. But again, I'm just telling you, if you use a variation like that, linear variation, then the contours of a linear function are always lines. These are the different, this is a family of contours, right, in each triangle. varying from 1 down to 0. They're always lines. And here the contours for a varying value of t within each triangle are conic sections of some type. Okay? And again, you can go higher, that they become even more complicated. Again, the correct image will depend on what the underlying physics says. And oftentimes we do not worry about that, but I want you to think about that and pay more attention to that. Alrighty, let's see. Just want to motivate that. Why is this important? Who has done volume rendering and ray casting? Ray casting, okay? When you did this for the first time, you did a volume rendering of a skull, or a volume rendering of a knee or hip or whatever, or heart, whatever you did. What do you see in those pictures?
It depends on your transfer function for volumes. I mean, if you're just getting the first value, it's whatever the intensity value is.
Do you always get beautiful, smooth, clean-looking pictures? No. What were your first impressions when you did your first volume renderer?
Well, depending on your transfer function, depending on what you transfer function.
See? Didn't really know what to look for, I guess. I got a picture and I saw that it was the outline of the soul, but inside it wasn't really useful. I had to.
Okay, I give you a different. If you do a volume rendering of a geometry that is a perfect sphere, I can give you a function where the contours would be perfect spheres mathematically, right? If you were to sample this perfect spherical function x squared plus y squared plus z squared equals radius from the center, then all the contours mathematically would be perfect spheres. That's not what we can do in volume rendering. In volume rendering, we have cells. We have Cartesian cells, 0, 1, 2, 3, 4, 5, and then we operate on the cells, right? So if I give you this sampled version of the perfect spherical contour, and you do a volume rendering of that, what will you get? What will you see in the picture of a perfect sphere?
Little cubes.
You will see artifacts, right? Okay. If you take a function like x squared plus y squared plus z squared equals radius squared, sample that onto a grid of 256 cubed, and you do the most basic volume render of that, you will see a bunch of little circular rings. You will see rings. There will be artifacts there where you see a pattern. Why does this pattern happen? What is the pattern is a consequence of what? These patterns you see are a consequence of the normal varying. In the volume rendering, you need a lighting model, right? You need to compute colors, and when you compute colors, that depends on certain vectors between the normal of the surface. There's some surface there, right? And you see there is a jump in the normal, right? Here it goes like this, and here it goes like that. Here's a jump. Therefore, these jumps here will mean, in volume renderings, you see these concentric patterns, always, okay? Unless you do something like that, or even something better. That's why we worry about that. Okay. If you use high resolution, super high resolution, then you don't see it even with this, of course. It's a matter of resolution too. Right? Once you super sample, then also you're not going to see it. All right. Scalar data, triangle-based, mesh-based. Okay. So we need to talk about this. Interpolation. Interpolation schemes. Interpolation schemes, one very important one is called scattered data interpolation. Scattered data interpolation, int. Okay. How does that work? Conceptually, you have samples in some space, domain space, x, y, z, and time, but I will stop at x, y. And you have locations with associated sticks or values. living above this plane where things were measured. If you make a picture, you can make a picture of sticks, and that's the truth. That's what you have. You don't have more. This is really all there is. Unless you have an understanding of the physics and you know how to put a continuum through there. Right? So that's what we assume, that you know how to properly interpolate this stuff, and you can produce a rendering like this. Okay? Where these lines that I've drawn are actually going or passing through these measurements, right? How do you get this function back from the sticks, right? So given is a set of these xi, yi, fi's, and output is some function f of xy such that st is always such that f, when I evaluated one of the original locations, xi, yi, returns the value there, fi, right? This is one of those locations, xi, yi, and this height there is the function value, fi. Right, so the surface that I compute has to satisfy this condition. This is the scattered setting. I consider nothing but the original locations and construct this function capital F. And there are two methods that we will talk about more and more to do this. And one is called Shepard's method, Shepard's, and the other is called Hardy's method, Hardy's method. This guy invented this when he was an undergraduate student, I think at the age of 16 or 17. Here in the States. I forgot the university. But look him up, okay? Look him up. Shepard's method, scattered data interpolation, and go to the original paper. Here, this when you find it. Okay, so that's how we do that. Now, when I do that without a mesh, shoot? Is there a difference?
Yeah, or which one is better?
Oh, I don't know. When is a method better? A method can be better if it is more general, if it is more specialized, if it is more robust, more numerically handleable, more efficient, computationally more efficient, real time, slower but more robust, depends on that. Right? What is better? Alternatives for different purposes. This is in general much more expensive, but produces better pictures. This is generally faster, but produces worse pictures on the highest level. Okay, so yes, Hardy's is better. But there are ways to make Shepard's also a better Shepard. The original version that this undergraduate student envisioned is really very bad. But then it was improved. So there's Shepard 2, Shepard 3, Shepard 17, and then it gets very good. And this one also, there's 50 variations on those. Hundreds of papers written on that. So then there are mesh-based methods. Mesh-based interpolation. Okay. The most important one is triangle-based. I hope that you don't mind my way to write sometimes. Triangle-based. It's okay? It's okay? Okay. So what do I mean? Triangle-based, obviously, you have an x and y and an f. And you have a bunch of points here. And so triangle-based means I connect these points first before I do anything with triangles. And what again do I have? Well, yes, I have more triangles, right? This goes on and on. And above the triangle, I have my sticks, my values, right? And over each triangle, I will construct one of those functions. There's this function f, lives everywhere. And now this function will be constructed for each triangle independently. Okay? Okay, so. Get the idea? They are triangle patches living over each triangle. So the entire function will be the collection or the union of all these triangle surfaces. Okay? So if I can do that, then there is also a more general version, which is based on natural neighbor computation. Which comes from geography. Natural neighbor. Neighbor interpolation. And what are natural neighbors? And this is also related to so-called Warner diagrams. And so how does this work? What's the natural neighbor? I give you a bunch of locations. Where do you drive shopping? I drive shopping to the city that is closest and has at least 100,000 inhabitants. So therefore, I will drive shopping when I live in Davis to what town? When I go shopping, I need to go to a city that has at least 100,000 inhabitants, and I live in Davis. So where do I go shopping? In Sacramento. I live in Berkeley, okay? I live in Berkeley, and when I go shopping, I have to go to a city that has at least 100,000 inhabitants. Where do I go shopping? Oakland, probably, right? Unless Berkeley already has 100,000, I don't know. So this is natural neighbor. This concept of Warner diagrams or Thiessen tessellations or Dirichlet tessellations comes from geography, where people in geography actually wanted to understand the influence of a metropolitan area on the surrounding neighborhoods. So therefore, you can actually show that the area or region of influence of a particular megacity is related to this thing or can be described by this thing. That's where this comes from. So now I draw you this particular diagram, and I show you where the cities are. Well, the cities are the circles, right? And okay. If I live anywhere in this region, and these circles are the cities of 100,000 people, then whenever I live in this region, where will I go shopping? There, right? Because that's the circle closest to me. So this is called the tile, right? This is called, this is the point P, and this is the tile of P. And these guys are the so-called natural neighbors of P. And when I compute a function, right, there's a function coming out of the board. I have function values here at these. When I compute a value, then I only consider the value of P and its natural neighbors. Okay, so this will become much more involved and more complicated. But this Warner diagram is very nice because it handles arbitrary arrangements of points, okay, scalar points. Let me see. I want to talk about data reduction and animation, data reduction and structure to finish. Particularly sensors or sensor networks or sensor nets are producing increasingly high-resolution data sets, okay, at shorter and shorter time intervals and at higher and higher spatial resolution. Therefore, you need to worry about which of all these measurements to store and analyze. So I just allude to the general problem, which we talk much more about, as data reduction, okay? Data reduction will be a very important topic. How can we think about that? Well, we can think about it as there's a spatial variable x, and in f direction I have a bunch of measurements. And I measure and measure and measure happily away, get all these happy measurements. Too much. There's too many data. I can't make a picture of it, right? Therefore, how can I reduce it? What does your eye see? Your eye sees, I can approximate this probably with a line, maybe with another line, right? Huh? More or less. There's a line here, there's a line. I could probably do this. I could say I start something here, I end something here, and then maybe go to there. If I only knew these 4 locations, then I could probably do something like this. Have one line, have one line and have another line. Okay? And if I evaluate these lines, I can nearly reproduce the original sticks. Right? That's the idea. So to get this, to get this, to get this, to get this. Right? So these individual measurements was a huge set of xi's and fi's. And this was huge. Okay? But these sticks, I mean, these lines are now only 3. How do I get them? What do I need to compute? I need to compute 2 things, right? I need to compute the set of these guys, right? Huh? From 1, 2, 3 to only 4. How do I get them? From 1 to 4. And I need to compute 1, 2, 3, the 4 circles, the values of those lines. How do I get those, right? Right? And the question is, how do I get them, right? Now, the same thing generalizes also for the room. If I have a high-density sensor network in this room or in this building, and I have 1 million sensor readings, and they measure 20 times every second, right, at 1 millimeter resolution, ultimately we will be able to do that, then what? It's too high resolution, right? Need something like that. You need this for univariate data. You need this for surface data. When you are scanning a car, an automobile, whatever surface it is you scan, human body, whatever, geometry. And ultimately, when you scan a field, a temperature field in a building, a temperature field in the ocean, a temperature field of the atmosphere, right? Many data. How do you bring it down to the essence? Well, the essence of this shape is these 3 lines. Boom. If you make sure that this always is smaller than some epsilon, right? So there is some tolerance there. You can guarantee that no original data value is more than epsilon away, then these lines are good enough, period. That's that. And now I talk about structure, and then I will hand you out your first reading assignments. Structure or topology. Okay. Where does this come from? This comes from mathematics. And from mathematical topology, the analysis of functions or their graphs and their behavior. 1D example, and you remember this from high school. If I give you an axis on your high school exit exam, you always were asked this following question: given this particular function, determine whether this function has what? What did you have to determine when this function was given to you as a cubic polynomial? Find its zeros and find its min and max and find its inflection point. Okay, something like that. Okay, you always have to find where does the graph of this function or this function have its zeros, where does it have its extrema, this guy and this guy, and where does it have its inflection point, right? Here it is right curved, and then it is left curved, right? Right? Right curvature, left curvature, correct? So there is an inflection point somewhere here. Okay? So you need the zeros, you need the extrema, and you need the inflection point. Inflection point. Okay. This is for a 1D function. Does the same hold for 2D functions? Well, since I asked that way, of course, right? For 2D, you have the same thing. For 2D, you have functions that look like that. And here is probably a local maximum there. The way I've sketched that, well, this is a sketch of x, y, and f going up, right? So there is some kind of local max. But this is more complicated probably to determine than to determine that thing, right? Is it? Is it not? Yet it is. Then you also have situations like these, where things look like that in this direction, and they look like this in the other direction. And this guy in the middle there also has a name. It's called a saddle point. Why? We saddle because it's like a saddle that you can sit in. So, saddle point. So, that's that. Last but not least, we need this for flow visualization. FlowViz. And I'll just give you a simple example. And many of you have already computed beautiful streamlines and trajectories like that. If I give you, say, an airfoil wing like this, then there's a bunch of vectors, a bunch of flow vectors around it. You can make beautiful Lick images, line integral convolution, trajectories, streamlines, all of that. But essentially what matters is how is this domain, this square, this xy square, separated into distinct regions. And it could be separated like this, for example. This is one possible way. Two go in, two come out. This detaches, and so forth. This and these points, these are critical points, characterizes the entire flow. That's all that's necessary. The rest is just pretty picture. Why? Why does this characterize everything? In this general area, this is a segment, right? You can look at this as one entire region. And in this entire region, you know how the flow behaves. The flow must behave like this. It has no choice but to behave like that. In this entire region here, the flow must behave like this. It has no choice but to behave like that. So in order to get to higher levels of abstractions, you do not compute all the streamlines, you just compute these things. Okay, these are so-called flow field separators. Flow field separators, because they separate the rectangle. Separators, separatrices, female separatrices. Okay, that's it for tonight. Bye-bye, Livermore. See you next Thursday night. And don't run away. Here are all your articles to read. And these are the articles for the whole quarter, okay? So don't be afraid.